The floor you stand on is not solid ground. It is the frozen surface of a 4 billion-year-old river of fire. And tonight, the Earth is finally ready to whisper the secrets it has spent eons trying to tell. Beneath your feet, 6,000 kilometers down, there exists a sphere of iron so hot it glows white even in absolute darkness. This is the inner core, a solid ball suspended in an ocean of molten metal, spinning at its own rhythm, slightly faster than the planet's crust. The pressure here is 3 million times greater than the air you breathe. At this depth, iron behaves in ways that defy the physics of the surface world. It crystallizes into structures that should not exist, aligned by magnetic forces older than continents, older than oceans, older than the first breath of oxygen that ever touched this world. The temperature exceeds 5,000 degrees Celsius, hotter than the surface of the sun, yet the iron remains solid, compressed by the unimaginable weight of an entire planet, bearing down upon a sphere no wider than the moon. This is the paradox at Earth's center, a furnace that cannot melt, a star that cannot shine, a heart that beats in slow magnetic pulses that ripple outward through 4 billion years of accumulated stone. Surrounding this inner sphere lies the outer core, 2,000 kilometers of liquid iron and nickel, churning in vast convective currents that have never known stillness. This is where Earth's magnetic field is born. The motion of molten metal generates electrical current, and these currents birth magnetic fields that wrap around the planet, like invisible armor, deflecting the solar wind, preserving the atmosphere, making life possible. Without this churning heart of liquid iron, the sun's radiation would have stripped away the oceans 3 billion years ago. Mars lost its magnetic field, its water evaporated into space. Earth kept spinning, kept churning, kept protecting. The outer core does not flow like water. It moves in patterns governed by the Coriolis effect, twisted by the planet's rotation into spiraling columns of molten metal that rise and fall in cycles lasting thousands of years. These columns are wider than mountain ranges. They carry heat from the inner core toward the mantle above, and in their movement, they generate the magnetic field that compasses have followed for centuries, that birds navigate by, that auroras paint across polar skies in curtains of green and violet light. Every 500,000 years, on average, something extraordinary happens. The magnetic field weakens, flickers, and reverses. North becomes south. South becomes north. The transition takes 1,000 years, a geological eye blink. During these reversals, the magnetic field does not vanish entirely, but it fragments into multiple poles, chaotic and unstable, offering less protection from cosmic radiation. Life endures. It always has. The last reversal occurred 780,000 years ago. We are overdue. The field is weakening now, measurably year by year. The next reversal is coming, written in the slow mathematics of fluid iron. Above the outer core lies the mantle, a layer of rock nearly 3,000 kilometers thick, comprising 84% of Earth's volume. This is not the solid, unyielding stone of human intuition. The mantle flows. Over millions of years it behaves like an extraordinarily viscous fluid, deforming under pressure and heat, convecting in vast cells that drive the motion of tectonic plates above. The rock here is so hot it glows a deep red, though no eye will ever witness it. Temperatures range from 1,000 degrees Celsius near the top to nearly 4,000 degrees at the boundary with the outer core. The mantle is composed primarily of silicate minerals, olivine, pyroxene, garnet, compressed into crystal structures that exist nowhere on the surface. At certain depths, the pressure is so immense that atoms rearrange themselves into denser configurations. Olivine transforms into wadsleyite at 410 kilometers depth. Wadsleyite becomes ringwoodite at 520 kilometers. Ringwoodite breaks down into perovskite and ferropyroclase at 660 kilometers. These are the transition zones, boundaries where the very nature of matter shifts under the weight of a planet. The mantle convects in a pattern called whole mantle convection. Hot material rises from the core mantle boundary in massive plumes, some of them 1,000 kilometers wide, ascending over tens of millions of years. When these plumes reach the base of the lithosphere, they spread outward, cooling, eventually sinking back down in subduction zones, where tectonic plates dive back into the Earth's interior. This is the engine that powers plate tectonics, that builds mountains, that opens oceans, that recycles the surface of the world in cycles lasting hundreds of millions of years. But not all of the mantle participates in this grand convection. At the core mantle boundary, 2,900 kilometers below the surface, there exist regions of anomalous material, large low shear velocity provinces, or LLSVPs. These are continent-sized blobs of dense, possibly ancient rock that have resisted mixing for billions of years. One sits beneath Africa, another beneath the Pacific. They may be remnants of Earth's earliest crust, subducted and preserved in the deep mantle, or they may be accumulations of dense material from the core itself. Their composition remains unknown. Their persistence is undeniable. These deep mantle structures influence the plumes that rise above them. The Hawaiian hotspot, the Icelandic hotspot, the Yellowstone supervolcano, all trace their origins to mantle plumes rooted at the edges of these ancient, immovable provinces. The surface geography of Earth, the placement of volcanoes and island chains, is determined in part by structures that have not moved in 1 billion years, anchored at the bottom of the mantle like mountains in an inverted world. Seismic waves reveal the mantle's secrets. When earthquakes occur, they send vibrations through the entire planet. Primary waves compress and expand the rock as they travel. Secondary waves shear it side to side. By measuring how these waves slow down, speed up, or refract as they pass through different materials, seismologists have mapped the interior of the Earth in exquisite detail, constructing images of a world no human will ever visit. The mantle is not uniform. It is heterogeneous, textured, scarred by billions of years of subducted ocean floor, ancient tectonic plates that sank into the deep and now lie folded and compressed in the transition zone, ghostly slabs of basalt and sediment that once formed the floor of vanished seas. Some of these slabs have been subducted so deeply they have reached the core mantle boundary. They lie there still, colder and denser than the surrounding mantle, influencing the flow of heat from the core, shaping the convection patterns that will in turn shape the surface continents 100 million years from now. The past is not erased. It is buried, preserved in the deep earth, a geological memory written in stone, and pressure, and time. The core mantle boundary is not a smooth surface. It is a landscape of inverted mountains and valleys, where the liquid iron of the outer core meets the solid rock of the lower mantle. The temperature contrast here is extreme, nearly 1,000 degrees across a boundary only a few kilometers thick. This is one of the most dynamic regions of the planet, a place where chemical reactions occur that may have been happening since the Earth first differentiated into layers 4.5 billion years ago. Iron from the core may react with silicates from the mantle, forming thin layers of exotic compounds, iron-rich post-perovskite, magnesio-woostite, materials that exist only under the crushing pressures of the deep earth. These reactions release heat, contribute to the mantle's convection, and may even influence the generation of the magnetic field. The core mantle boundary is not a passive interface. It is a forge, a reactor, a place where the planet continuously remakes itself on timescales beyond human comprehension. Rising from this boundary are the superplumes, massive upwellings of hot mantle rock that ascend through the entire mantle over tens of millions of years. These are not the narrow plumes that feed individual volcanoes. These are structures hundreds of kilometers wide, carrying enough heat to thin the lithosphere above them, to crack continents apart, to flood entire regions with basaltic lava. The Siberian traps, the Deccan traps, the Columbia River basalts, all are the surface expressions of superplumes that originated at the core mantle boundary. When a superplume reaches the base of the lithosphere, it does not simply erupt. It spreads outward, pooling beneath the crust, heating it from below, causing it to dome upward. Rifts form. Magma intrudes. Eventually, if the plume persists, the continent fractures. A new ocean basin is born. This is how the Atlantic Ocean began. A mantle plume beneath Pangaea, heating the supercontinent from below until it split along a line that would become the Mid-Atlantic Ridge. The plume is still there, beneath Iceland, still feeding the volcanic activity that builds the island higher with each eruption. The mantle is not silent, it hums. Seismometers detect a continuous background vibration, a low-frequency oscillation that permeates the entire planet. This is the Earth's hum, generated by the constant motion of ocean waves, by atmospheric pressure changes, and by the slow grinding convection of the mantle itself. The frequency is far below the range of human hearing, but it is always present, a planetary heartbeat that has never stopped since the oceans first formed. Within the mantle there are diamonds, not the small gemstone-quality crystals found in kimberlite pipes, but massive ancient diamonds formed in the transition zone, 400 to 600 kilometers deep, where carbon is subjected to pressures that transform it into the hardest natural substance known. Some of these diamonds contain inclusions, tiny pockets of minerals trapped during crystallization. These inclusions are windows into the deep earth, preserving samples of mantle rock that would otherwise be inaccessible. Ringwoodite inclusions have been found containing water, not liquid water, but hydroxyl ions bonded within the crystal structure. This suggests that the mantle's transition zone may hold more water than all the oceans on the surface combined, locked within minerals, hidden, patient, waiting. The mantle is also a graveyard. Every tectonic plate that has ever subducted into a trench has descended into the mantle, carrying with it the sediments of ancient ocean floors, the fossils of creatures that lived and died hundreds of millions of years ago, the chemical signatures of atmospheres long since transformed. These materials do not vanish. They are recycled, mixed into the mantle's convection, and eventually return to the surface through volcanic eruptions. The carbon dioxide released by volcanoes today may have been part of a coral reef in the Devonian. The water vapor in a fumarole may have been seawater when trilobites crawled across the ocean floor. This is the mantle's role: to recycle, to preserve, to transform. It is the planet's memory, storing the history of the surface world in its depths, releasing it slowly, incrementally, through the patient work of convection and volcanism. The mantle does not forget. It archives every subducted plate, every vanished ocean, every extinct species whose remains were carried down into the deep. And in time, over hundreds of millions of years, it returns them, altered, reborn, as new crust, new mountains, new continents. The heat that drives all of this, the convection, the plumes, the subduction, comes from two sources. Half of it is primordial heat, left over from the planet's formation, from the collisions of planetesimals that built the Earth 4.5 billion years ago, from the differentiation event when iron sank to the core and released gravitational potential energy as heat. This heat is still radiating outward, still escaping into space, but so slowly that the mantle has cooled by only a few hundred degrees since the Archean. The other half comes from radioactive decay, uranium, thorium, and potassium embedded in the mantle's minerals. decay over billions of years, releasing heat as their atoms break apart. This is the Earth's internal furnace, a nuclear reactor that has been running since the planet formed and will continue running for billions of years to come. The decay is slow, but the quantities are vast. The mantle contains enough radioactive elements to power its convection for the entire lifespan of the Sun. Without this heat, the mantle would solidify, convection would cease, plate tectonics would stop, the magnetic field would collapse, the surface would become geologically dead, like Mars, like Mercury, like the Moon. But the heat endures, and so the mantle flows, and so the Earth remains alive, dynamic, ever-changing. The mantle plumes that rise from the core mantle boundary do not ascend in straight lines. They are deflected by the convection currents of the surrounding mantle, twisted by the planet's rotation, shaped by the density variations of subducted slabs. Some plumes are stationary, anchored to the core mantle boundary for hundreds of millions of years, creating hotspot tracks as tectonic plates move over them. The Hawaiian Emperor Seamount Chain, the Yellowstone Caldera Track, the Réunion Hotspot Trail. Others are transient, rising once and then dissipating, leaving behind flood basalts and large igneous provinces that mark moments of catastrophic volcanism in Earth's history. The mantle is patient. It moves at the speed of fingernail growth, a few centimeters per year. But over geological time, this is enough to reshape the entire surface of the planet, to close oceans and open new ones, to build mountain ranges and erode them back to plains. The mantle is the engine of geology, the force that makes Earth a living world, and it will continue its slow, inexorable work long after humanity is gone, long after the last ocean has evaporated, until the sun expands into a red giant and consumes the planet entirely. But for now, tonight, the mantle flows. The core spins, the magnetic field holds, and the Earth, ancient and patient, continues to whisper its secrets to those willing to listen. The continents are not anchored. They drift across the surface of the planet at the speed of growing hair, riding on slabs of lithosphere that fracture, collide, and sink back into the mantle in a cycle that has repeated for at least 3 billion years. This is the dance of the drifting giants, a slow-motion ballet choreographed by convection currents in the mantle below, a performance that builds mountains, opens oceans, and periodically assembles all the world's land masses into a single, colossal supercontinent. The lithosphere, the rigid outer shell of the Earth, is broken into 7 major plates and dozens of smaller ones. These plates are not uniform. Oceanic lithosphere is thin, dense, and young, rarely older than 200 million years. Continental lithosphere is thick, buoyant, and ancient, with some fragments dating back nearly 4 billion years. The plates float on the asthenosphere, a layer of partially molten ductile mantle rock that deforms over geological time, allowing the plates above to slide, grind, and collide. At divergent boundaries, plates pull apart, magma wells up from the mantle to fill the gap, solidifying into new oceanic crust. The Mid-Atlantic Ridge is the longest mountain range on Earth, stretching 16,000 kilometers from the Arctic to the Southern Ocean, hidden beneath 2 kilometers of seawater. Here, the Eurasian and North American plates separate at a rate of 2.5 centimeters per year. The ridge is not a smooth line, but a fractured, segmented scar, offset by transform faults where the plates slide past each other in sudden, violent jerks that register as earthquakes. The new crust formed at mid-ocean ridges is basaltic, dark and fine-grained, erupted from fissures in the seafloor in pillow-shaped lobes that cool instantly upon contact with frigid ocean water. This basalt is magnetized by the Earth's magnetic field at the moment of its solidification, preserving a record of the field's orientation. As new crust forms and pushes older crust away from the ridge, It creates symmetrical stripes of alternating magnetic polarity on either side, a geological barcode that records every magnetic reversal for the past 200 million years. At convergent boundaries, plates collide. When oceanic lithosphere meets continental lithosphere, the denser oceanic plate subducts, diving beneath the continent and descending into the mantle. The Nazca Plate subducts beneath South America, generating the earthquakes and volcanoes of the Andes. The Pacific Plate subducts beneath Japan, creating the deep ocean trenches and explosive volcanic arcs that define the Ring of Fire. Subduction is not smooth. The descending plate sticks, accumulates stress, and then releases it in megathrust earthquakes, the most powerful seismic events the planet can produce. When two continental plates collide, neither subducts. Both are too buoyant, too thick, too resistant to being dragged down into the mantle. Instead, they crumple, fold, and thrust upward, building mountain ranges that rise kilometers into the sky. The Himalayas are the result of the Indian plate colliding with the Eurasian plate, a collision that began 50 million years ago and continues today. India is still pushing northward at 5 centimeters per year, and the Himalayas are still rising, though erosion removes rock almost as quickly as tectonics can lift it. At transform boundaries, plates slide past each other horizontally. The San Andreas Fault is a transform boundary where the Pacific Plate grinds past the North American Plate. There is no volcanism here, no creation or destruction of crust, only lateral motion, slow, relentless, punctuated by earthquakes when friction is overcome and the plates lurch forward in sudden, catastrophic slips. Los Angeles, riding on the Pacific Plate, is moving towards San Francisco on the North American Plate, at a rate of about 5 centimeters per year. In 15 million years, they will be neighbors. The motion of tectonic plates is driven by several forces. Ridge push occurs at mid-ocean ridges, where newly formed elevated crust slides downhill away from the ridge axis under the influence of gravity. Slab pull is the dominant force, the weight of cold, dense oceanic lithosphere sinking into the mantle at subduction zones, dragging the rest of the plate behind it. Mantle convection provides the underlying engine, with rising plumes and descending slabs creating a circulation pattern that moves the plates above. The forces are interconnected, each reinforcing the others, creating a self-sustaining system that has operated for billions of years. But the configuration of plates has not been constant. Continents have drifted, collided, and fragmented repeatedly throughout Earth's history. Supercontinents form and break apart in a cycle known as the Wilson cycle, named after the geophysicist who first proposed it. The cycle takes approximately 500 million years. A supercontinent assembles through the collision of smaller landmasses. It remains stable for a time, but the insulating effect of such a large landmass traps heat in the mantle below. Eventually, the trapped heat causes the supercontinent to dome upward, rifts form, and the landmass fractures. New ocean basins open. The fragments drift apart. Eventually, subduction zones consume the old ocean floor, and the continents are drawn back together, forming a new supercontinent in a different configuration. Pangaea is the most recent supercontinent, assembled around 300 million years ago during the late Paleozoic. It was not the first. Before Pangaea, there was Panatonia, formed around 600 million years ago. Before Panatonia, there was Rodinia, assembled around 1 billion years ago. Before Rodinia, the record becomes fragmentary, but evidence suggests that supercontinents have been forming and breaking apart for at least 2.5 billion years, possibly longer. Pangaea was a C-shaped landmass that stretched from pole to pole, surrounded by a single vast ocean called Panthalassa. The interior of Pangaea was arid, cut off from moisture-bearing ocean winds by the sheer distance from the coast. Deserts dominated the continental interior, The climate was extreme, with scorching summers and frigid winters. The Appalachian Mountains, the Scottish Highlands and the Anti-Atlas Mountains of Morocco were all part of a single continuous mountain range formed by the collision of Laurentia Baltica and Gondwana. Within the embrace of Pangaea's sea shape lay the Tethys Sea, a tropical ocean that would eventually close as Africa rotated northward. Its sediments crumpled and uplifted to form the Alps, the Carpathians and the Himalayas. The Tethys is gone now, reduced to remnants, the Mediterranean, the Black Sea, the Caspian. But its legacy is written in the limestone peaks of southern Europe and the fossil-rich strata of the Tibetan Plateau. Pangaea began to fracture around 200 million years ago, during the early Jurassic. The first rift opened between North America and Africa, initiating the formation of the Atlantic Ocean. The rift propagated northward and southward over tens of millions of years, unzipping the supercontinent along a line that would become the Mid-Atlantic Ridge. Basaltic magma flooded the rift valleys, forming the Central Atlantic Magmatic Province, one of the largest volcanic events in Earth's history. The eruptions released vast quantities of carbon dioxide, triggering climate change and mass extinction at the end of the Triassic. As Pangaea fragmented, the pieces drifted apart, carried by the spreading seafloor. South America separated from Africa around 130 million years ago. India broke away from Antarctica and Madagascar, racing northward across the Tethys Sea at speeds exceeding 15 centimeters per year, extraordinarily fast by geological standards. Australia remained attached to Antarctica until around 50 million years ago, when it finally separated and began its journey towards Southeast Asia. The breakup of Pangaea was not a single event, but a prolonged process of rifting, volcanism, and seafloor spreading that reshaped the planet's geography over 200 million years. The Atlantic Ocean widened, the Pacific Ocean shrank. New subduction zones formed along the western coasts of the Americas as the Atlantic pushed the continents westward, overriding the Pacific seafloor. The Andes rose, the Rocky Mountains uplifted, the Ring of Fire ignited with volcanic arcs and deep ocean trenches encircling the Pacific Basin. The continents continue to drift. Africa is moving northward, closing the Mediterranean Sea. In 50 million years, the Mediterranean will be gone, replaced by a mountain range stretching from Spain to Iran as Africa collides with Europe. The Atlantic continues to widen, pushing the Americas away from Europe and Africa at a rate of a few centimeters per year. The Pacific is shrinking, consumed by subduction zones along its margins. Australia is drifting northward, on a collision course with Southeast Asia. In the deep future, these motions will culminate in the formation of a new supercontinent. Geologists have named this future supercontinent Pangaea Ultima, though its exact configuration is uncertain. One model suggests that the Atlantic will begin to close, bringing the Americas back into collision with Europe and Africa, reassembling a Pangaea-like landmass. Another model, called Amarcia, predicts that the continents will converge around the North Pole as the Arctic Ocean closes. A third model, Orica, envisions a new supercontinent forming as both the Atlantic and Pacific close, with a new ocean basin opening through the middle of the current landmasses. The details are speculative, but the inevitability is not. The continents will collide again. A new supercontinent will form, and eventually it too will break apart. The evidence for continental drift was first compiled by Alfred Wegener in the early 20th century. He noticed that the coastlines of South America and Africa fit together like puzzle pieces. He found identical fossil species on continents now separated by thousands of kilometers of ocean. Mesosaurus in South America and Africa, Glossopterus flora in South America, Africa, India, Antarctica, and Australia, Lystrosaurus in Africa, India, and Antarctica. He documented matching geological formations and mountain ranges on opposite sides of the Atlantic. But Wegener could not explain the mechanism. He proposed that continents ploughed through the oceanic crust, like ships through ice, a notion that physicists rightly rejected as impossible. The mechanism was discovered in the 1960s through the study of the ocean floor. Magnetic surveys revealed the symmetrical stripes of alternating polarity flanking mid-ocean ridges. Seismology mapped the distribution of earthquakes along plate boundaries. Deep-sea drilling confirmed that oceanic crust is youngest at the ridges and progressively older toward the continents. The theory of plate tectonics emerged, synthesizing these observations into a coherent framework that explained not only continental drift, but also earthquakes, volcanoes, mountain building, and the distribution of mineral resources. Plate tectonics is unique to Earth. Venus, similar in size and composition, has no plate tectonics. Its surface is dominated by volcanic plains and is resurfaced episodically by massive volcanic events rather than continuous recycling. Mars once had tectonic activity, evidenced by the Valles Marineris rift system, but its lithosphere is now a single rigid shell. The Moon, Mercury, and the moons of the outer planets are geologically dead or driven by processes other than plate tectonics. Tidal heating in the case of Io and Europa, cryovolcanism on Enceladus and Triton. Earth's plate tectonics may be enabled by the presence of water. Water lowers the melting point of mantle rock, facilitating the formation of magma and the lubrication of subduction zones. Water also weakens minerals, allowing the lithosphere to fracture and deform. Without water, the lithosphere might be too strong to break into plates, too rigid to subduct. The oceans, then, are not merely a surface feature but an integral component of the tectonic system, cycling through the mantle via subduction and returning to the surface through volcanic outgassing. Subducted water is carried down into the mantle, within hydrated minerals, serpentine chlorite amphibole. At depths of around 100 kilometers, these minerals break down, releasing water into the overlying mantle wedge. The water triggers partial melting, generating the magmas that feed volcanic arcs. Some water is released at shallow depths, but some is carried deeper, into the transition zone and perhaps even to the lower mantle. The water content of the deep mantle is unknown, but inclusions in deep diamonds suggest that significant quantities of water may be stored in the mantle's interior, locked within high-pressure mineral phases. The tectonic plates are not eternal. Oceanic lithosphere is continuously created and destroyed, recycled through the mantle in a process that takes around 200 million years. Continental lithosphere, being buoyant, resists subduction and accumulates over billions of years. The oldest oceanic crust is found in the Western Pacific, around 200 million years old. The oldest continental crust is found in the Canadian Shield, the Pilbara Craton of Australia, and the Karpval Craton of South Africa, with ages exceeding 3.5 billion years. These ancient cratons are the nuclei of the continents, stable blocks of Archean crust that have survived multiple supercontinent cycles. They are composed of granite and metamorphosed volcanic rocks, formed in the early Earth when the mantle was hotter and tectonic processes operated differently. The cratons are thick, cold, and strong, extending down into the mantle as deep keels that anchor the continents and resist deformation. Surrounding the cratons are younger terrains, fragments of island arcs, oceanic plateaus, and microcontinents that have been accreted onto the cratons over billions of years, building the continents outward like layers of sediment. The continents grow, but they also erode. Rivers carry sediment from the mountains to the oceans. Wind scours the deserts. Glaciers grind bedrock into powder. The eroded material accumulates on continental shelves and in deep ocean basins, eventually to be subducted and recycled into the mantle, or accreted onto the continents as new terrains. The balance between growth and erosion determines the long-term evolution of continental crust. Currently, the continents are growing slowly, but the rate varies over geological time. The drifting of continents has profound effects on climate. When continents are clustered near the equator, they absorb solar radiation and heat the planet. When continents are positioned over the poles, ice sheets form, reflecting sunlight and cooling the planet. The opening and closing of ocean gateways alters ocean currents, redistributing heat around the globe. The uplift of mountain ranges affects atmospheric circulation and precipitation patterns. The Himalayas, for example, block moisture from reaching Central Asia, creating the arid conditions of the Tibetan Plateau and the Gobi Desert. The uplift of the Himalayas also accelerated the weathering of silicate rocks, drawing down atmospheric carbon dioxide and contributing to the global cooling that led to the current ice age. Plate tectonics is the mechanism by which the Earth regulates its climate over geological time. Volcanic outgassing releases carbon dioxide into the atmosphere. Weathering of silicate rocks consumes carbon dioxide, locking it into carbonate minerals that are eventually subducted and returned to the mantle. This cycle, known as the carbonate-silicate cycle, operates over millions of years and acts as a planetary thermostat, stabilizing Earth's climate and making long-term habitability possible. The plates drift, the continents collide and fragment, the oceans open and close. And through it all, the Earth remains dynamic, alive, continuously reshaping its surface in a slow, patient rhythm that has persisted for billions of years and will continue for billions more. Deep within the Earth, where pressure and time converge in absolute darkness, atoms arrange themselves into geometries of perfect order. These are the crystals, silent architectures built one molecule at a time over millions of years, structures so precise they seem to defy the chaos of the molten world that surrounds them. They grow in cavities and fractures, in cooling magma chambers and metamorphic depths, each one a frozen moment of geological patience, a testament to the slow mathematics of mineral formation. A crystal is not merely a pretty stone, it is a lattice, a three-dimensional repeating pattern of atoms locked into position by electromagnetic forces. The arrangement determines everything: the hardness, the color, the way light bends and fractures as it passes through. Quartz arranges silicon and oxygen into hexagonal prisms. Halite, common salt, forms perfect cubes. Pyrite crystallizes into octahedrons and dodecahedrons, its brassy surfaces catching light like fragments of a shattered sun. The geometry is not random. It is dictated by the atomic structure of the mineral, by the angles at which chemical bonds form, by the symmetry inherent in the arrangement of electrons. Crystals grow from solutions, molten rock, mineral-rich water, vapor. As the solution cools or evaporates, atoms begin to settle out, attaching to a seed crystal or nucleating spontaneously. The first atoms to attach establish the pattern. Subsequent atoms follow layer by layer, building outward in all directions, maintaining the symmetry of the original lattice. Growth is slow. A crystal the size of a human hand may take 1 million years to form. Larger crystals take longer. The giant gypsum crystals of the Nika mine in Mexico, some of them 11 meters long and weighing 50 tons, grew over 500,000 years in a water-filled cavern heated by magma below. The temperature held steady at 58 degrees Celsius. The solution saturated with calcium sulfate. The conditions perfect and uninterrupted for eons. The Nika crystals are selenite, a transparent variety of gypsum. They are so large that humans can walk among them, though the heat and humidity of the cavern make prolonged exposure lethal. The crystals are flawless, their surfaces smooth and faceted, their interiors clear as glass. They are fragile despite their size. Gypsum is soft, easily scratched, soluble in water. When the mine was dewatered to allow access, the crystals began to degrade, their surfaces dulling, hairline fractures appearing as they adjusted to the dry air. They are relics of a specific set of conditions that no longer exist, preserved only as long as the cavern remains sealed and flooded. Not all crystals are fragile. Diamond is the hardest natural material known, a form of pure carbon in which each atom is bonded to 4 neighbours in a tetrahedral lattice. The bonds are covalent, extraordinarily strong, requiring immense pressure to form. Diamonds crystallize in the mantle at depths greater than 150 kilometers, where the pressure exceeds 50,000 atmospheres and the temperature exceeds 1,000 degrees Celsius. They are brought to the surface by kimberlite eruptions, violent, deep-sourced volcanic events that ascend from the mantle at speeds exceeding 100 kilometers per hour, carrying diamonds and other mantle xenoliths to the surface before they can transform back into graphite. Most diamonds are small, industrial grade, included with impurities and fractures. Gem-quality diamonds are rare. Flawless diamonds are rarer still. The largest diamond ever found, the Cullinan diamond, weighed over 3,000 carats in its rough state. More than 600 grams of pure crystallized carbon formed deep in the mantle beneath what is now South Africa, brought to the surface by a kimberlite eruption around 1 billion years ago, and discovered in 1905 in a mine that has since yielded some of the world's most famous gemstones. Diamonds are not the only gemstones formed under extreme conditions. Rubies and sapphires are varieties of corundum, aluminum oxide crystallized under high pressure and temperature in metamorphic rocks. The color depends on trace impurities, chromium for rubies, iron and titanium for blue sapphires. Emeralds are beryl crystals colored green by trace amounts of chromium or vanadium, formed in hydrothermal veins where hot, mineral-rich fluids percolate through fractured rock. Opals are not crystals at all, but amorphous silica formed from silica-rich water that seeps into cavities and evaporates, leaving behind microscopic spheres of silica that diffract light into iridescent flashes of color. The color of a gemstone is often the result of defects. Pure corundum is colorless. Pure quartz is colorless. It is the impurities, the trace elements substituted into the crystal lattice, the vacancies and dislocations in the atomic structure that absorb certain wavelengths of light and transmit others, giving the crystal its hue. Amethyst is quartz-colored purple by iron impurities and natural radiation. Citrine is quartz-colored yellow by heat-treated iron. Smoky quartz is darkened by radiation-induced defects in the silicon-oxygen lattice. The defects are not flaws but features, the signature of the crystal's formation history, the record of the conditions it endured. Some crystals form in geodes, hollow cavities lined with inward-pointing crystals. Geodes begin as gas bubbles in cooling lava, or as voids left by dissolved fossils in sedimentary rock. Over time, mineral-rich groundwater seeps into the cavity, depositing layers of silica or calcite on the walls. The crystals grow inward toward the center of the void, their termination sharp and well-formed because they grew freely, unobstructed by surrounding rock. Amethyst geodes from Brazil and Uruguay can be large enough to stand inside, their interiors encrusted with thousands of purple quartz crystals, each one a hexagonal prism terminated by a pyramid of facets. Crystals also form in pegmatites, coarse-grained igneous rocks that crystallize from the last water-rich remnants of a cooling magma chamber. Pegmatites cool slowly, allowing crystals to grow to exceptional sizes. Beryl crystals from pegmatites can exceed 10 meters in length. Spodumene crystals, lithium aluminum silicate, have been found weighing several tons. Pegmatites are the source of many rare minerals, including tantalum, niobium, and the rare earth elements, concentrated in the final stages of magma crystallization, when incompatible elements that do not fit into common minerals are forced into the remaining melt. The study of crystals is called crystallography. It began with the observation that crystals of the same mineral always exhibit the same angles between corresponding faces, regardless of size or distortion. This constancy of interfacial angles, first documented in the 17th century, revealed that crystals possess an underlying order, a hidden symmetry that governs their external form. The development of X-ray crystallography in the early 20th century allowed scientists to probe the atomic structure of crystals, revealing the precise arrangement of atoms within the lattice and establishing the field of solid-state physics. Crystals are not static. They respond to stress, to temperature changes, to the passage of time. Some crystals are piezoelectric, generating an electric charge when compressed. Quartz is piezoelectric, a property exploited in watches, sensors, and oscillators. Some crystals are pyroelectric, generating a charge when heated. Tourmaline is pyroelectric and also pleochroic, appearing different colors when viewed from different angles due to the anisotropic absorption of light. Crystals can also be twinned, two or more crystals intergrown in a symmetrical fashion. Twinning occurs when a crystal begins to grow in one orientation, then shifts to another orientation related to the first by a mirror plane or rotation axis. The result is a composite crystal with a distinctive shape. The cross-shaped twins of staurolite, the fishtail twins of gypsum, the elbow twins of rutile. Twinning is common in feldspars, the most abundant minerals in the Earth's crust, and can be used to identify different feldspar species under a polarizing microscope. Some minerals do not form well-defined crystals, but instead grow as fibrous masses, radiating clusters or botryoidal, grape-like aggregates. Asbestos minerals are fibrous, their crystals elongated into thin, flexible strands that can be woven into fireproof cloth. Malachite and hematite often form botryoidal masses, their surfaces rounded and smooth, built up layer by layer as mineral-rich water precipitates on the surface. These habits, the characteristic shapes and growth patterns of minerals, are determined by the conditions of formation, the rate of growth, and the availability of space. In caves, crystals grow from dripping water, stalactites hang from the ceiling, stalagmites rise from the floor, and where they meet, they form columns. These are not single crystals, but polycrystalline aggregates of calcite, deposited molecule by molecule, as water saturated with dissolved calcium carbonate drips through the cave, releasing carbon dioxide and precipitating calcite. The growth rate is measured in millimeters per century. The largest stalactites are tens of meters long, the product of hundreds of thousands of years of patient deposition. Ice is a crystal. Snowflakes are single crystals of ice, each one unique. Their six-fold symmetry a reflection of the hexagonal arrangement of water molecules in the ice lattice. The intricate branching patterns of snowflakes are determined by the temperature and humidity of the air through which they fall, each arm of the snowflake experiencing the same conditions and therefore growing in the same way, creating symmetry without central coordination. No two snowflakes are identical because no two follow exactly the same path through the atmosphere, but all share the same underlying hexagonal geometry. Salt crystals form when seawater evaporates. In shallow lagoons and salt flats, the concentration of dissolved salts increases until the solution becomes supersaturated and halite begins to precipitate. The crystals are cubic, their faces meeting at right angles, their edges sharp. In ancient evaporite basins, layers of halite hundreds of meters thick accumulated over millions of years, buried and preserved, later mined for table salt, road salt, and chemical feedstock. The Permian Basin of Texas and New Mexico contains vast deposits of halite and other evaporite minerals, the remnants of a shallow sea that evaporated 250 million years ago. Crystals can also form in living organisms. Calcium carbonate crystallizes in the shells of mollusks, the skeletons of corals, the tests of foraminifera. The crystals are not random but organized into intricate structures. The nacreous layers of abalone shells, the radial calcite of sea urchin spines, the aragonite needles of coral skeletons. These biogenic crystals are often stronger and more resilient than their inorganic counterparts, their growth mediated by organic molecules that control nucleation, orientation, and morphology. Humans have been fascinated by crystals for millennia. Ancient civilizations prized gemstones for their beauty and rarity, attributing to them mystical properties and healing powers. Diamonds were believed to confer invincibility. Rubies were thought to protect against poison. Emeralds were said to improve eyesight. These beliefs were unfounded, but the allure of gemstones persists, driven not by superstition but by aesthetics, the play of light within a faceted diamond, the deep red glow of a ruby, the shifting colors of an opal. The value of gemstones is determined by rarity, clarity, color, and size. Diamonds are graded on the 4 C's: carat weight, cut, color, and clarity. The most valuable diamonds are colorless, flawless, and expertly cut to maximize brilliance and fire. Colored diamonds, blue, pink, yellow, green, are rarer and often more valuable. The Hope diamond, a deep blue diamond weighing 45 carats, is colored by trace amounts of boron and is one of the most famous gemstones in the world, with a history spanning centuries and continents. Synthetic crystals can now be grown in laboratories. Synthetic diamonds are produced by subjecting carbon to high pressure and high temperature, mimicking the conditions of the mantle, or by chemical vapor deposition in which carbon atoms are deposited onto a substrate from a gas phase. Synthetic rubies and sapphires are grown by the vernule process, in which aluminum oxide powder is melted in a flame and allowed to crystallize on a rotating seed. These synthetic crystals are chemically and structurally identical to their natural counterparts, often more perfect, free of the inclusions and flaws that characterize natural gemstones. They are less expensive, but also less valued, because rarity and natural origin contribute to the perception of worth. Crystals are also used in technology. Silicon crystals are the foundation of the semiconductor industry, sliced into wafers and etched with microscopic circuits to create computer chips. Quartz crystals regulate the frequency of electronic oscillators, providing the timing signals for computers, phones, and GPS satellites. Liquid crystals, in which molecules maintain partial order while flowing like a liquid, are used in displays, their orientation controlled by electric fields to modulate the transmission of light. The modern world is built on crystals, their atomic precision harnessed for computation, communication, and control. In the deep earth, crystals continue to form, indifferent to human use or appreciation. Garnets grow in metamorphic rocks, their dodecahedral forms nestled in schist and gneiss. Olivine crystallizes in the mantle, its green crystals occasionally brought to the surface in basaltic lava. Zircon, one of the oldest minerals, forms in granitic magmas and resists weathering and metamorphism, preserving within its crystal lattice trace amounts of uranium that decay into lead, providing a radiometric clock that dates the formation of the crystal. The oldest zircon crystals, found in the Jack Hills of Western Australia, are over 4 billion years old, nearly as old as the Earth itself. Survivors of a time when the planet was still cooling, still forming, still finding its shape. Crystals are the Earth's memory, encoded in atomic arrangements that persist for billions of years. They record the temperature and pressure of their formation, the composition of the fluids from which they grew, the passage of time measured in radioactive decay. They are silent witnesses to the planet's history, each one a small, perfect archive of the conditions that created it. And they are beautiful, not because beauty serves a function, but because order and symmetry, repeated at the atomic scale and manifested in macroscopic form, resonate with something deep in human perception. The facets of a crystal catch light and split it into colors. The transparency of quartz reveals the interior, the growth zones and inclusions that map the crystal's history. The iridescence of opal shifts with the angle of view, a consequence of light diffracting through arrays of silica spheres too small to see. Crystals do not care that they are beautiful. They simply are. They grow in darkness, in silence, in the deep places of the earth, assembling themselves atom by atom according to the immutable laws of chemistry and physics, creating order from chaos, structure from solution, geometry from the formless depths. And when they are brought to the surface, when light touches them for the first time in millions of years, they shine. Mountains do not stand forever. The moment they rise, they begin to fall. Erosion is the patient dismantling of stone, the slow work of water, wind, ice, and gravity, carving the surface of the earth grain by grain, reshaping continents over millions of years. What tectonic forces build, erosion tears down, and in the contest between uplift and decay, the landscape is sculpted into forms of breathtaking complexity. Canyons that plunge kilometers into layered rock, arches that span desert voids, sand dunes that migrate across continents like frozen waves. Water is the most powerful sculptor. Rivers carve valleys, cutting downward through bedrock with the abrasive force of sediment-laden flow. The Grand Canyon is a testament to this power, a chasm nearly 2 kilometers deep, carved by the Colorado River over the past 6 million years. The river did not cut through the rock quickly. It worked grain by grain, carrying away particles of sandstone, limestone, and shale, exposing layers of rock that span nearly 2 billion years of Earth's history. The oldest rocks at the bottom of the canyon are Vishnu schist, metamorphosed sediments from an ancient ocean floor, formed nearly 2 billion years ago. The youngest layers at the rim are Kaibab limestone, deposited in a shallow sea 270 million years ago. Between them lie the pages of deep time, each layer a chapter in the geological narrative. The river does not work alone. Freeze-thaw cycles fracture the canyon walls. Water seeps into cracks, freezes, expands, and wedges the rock apart. Fragments tumble into the river and are carried downstream, ground into smaller and smaller pieces until they become sand, silt, and eventually dissolved ions carried to the ocean. The canyon widens as its walls collapse. Side canyons branch off, carved by tributary streams during flash floods. The landscape is not static, but continuously evolving, shaped by the interplay of flowing water and fractured stone. Waterfalls accelerate erosion, where a river flows over a resistant layer of rock underlain by softer material. The softer rock erodes faster, undercutting the harder layer until it collapses. The waterfall retreats upstream, leaving behind a gorge. Niagara Falls has retreated 11 kilometers over the past 12,000 years, since the end of the last ice age. The falls erode the underlying shale, and the overlying dolomite periodically collapses in massive blocks. Eventually, the falls will retreat all the way to Lake Erie, draining the lake and altering the geography of the Great Lakes region. Rain dissolves limestone. Carbon dioxide in the atmosphere combines with rainwater to form weak carbonic acid, which reacts with calcium carbonate in limestone, dissolving it and carrying it away in solution. Over millions of years, this process creates karst landscapes, regions riddled with sinkholes, caves, and underground rivers. The limestone plateaus of southern China, the Yucatan Peninsula, and the Dinaric Alps are karst terrains. Their surface is pockmarked with collapse features, and their subsurfaces honeycombed with caverns. Caves form where groundwater flows through fractures in limestone, dissolving the rock and enlarging the passages. The largest cave systems extend for hundreds of kilometers. Mammoth Cave in Kentucky is the longest known cave system in the world, with over 650 kilometers of surveyed passages. The cave formed over the past 10 million years as the Green River cut downward, lowering the water table and draining the limestone aquifer, leaving behind a labyrinth of dry passages decorated with stalactites, stalagmites, and flowstone. Wind is a sculptor in arid lands. Where vegetation is sparse and the surface is dry, wind picks up fine particles and carries them across the landscape. Sand grains are too heavy to be lifted high into the air, so they travel by saltation, bouncing along the surface in a series of hops. Each impact dislodges other grains, creating a cascading effect. Over time, wind-driven sand abrades exposed rock, carving ventifacts, stones with flat, polished faces aligned with the prevailing wind direction. Sand dunes are the most visible expression of wind's power. Dunes form where sand accumulates faster than it can be removed, building into ridges and mounds that migrate downwind as sand is blown up the gentle windward slope and avalanches down the steep leeward face. The shape of a dune depends on wind direction, sand supply, and vegetation. Barken dunes are crescent-shaped, with horns pointing downwind, common in areas with limited sand and unidirectional winds. Linear dunes are long, parallel ridges aligned with the wind, found in regions with strong, consistent winds. Star dunes have multiple arms radiating from a central peak, formed where winds blow from multiple directions. The largest sand seas, or ergs, cover vast areas of the Sahara, the Arabian Peninsula, and the deserts of Central Asia. The Rub al-Khali, the empty quarter of Arabia, is the largest continuous sand desert in the world, covering over 600,000 square kilometers. The dunes here can exceed 250 meters in height, their slopes rippled with smaller dunes, and their surfaces sculpted into intricate patterns by the wind. The sand is not static. The dunes migrate, advancing several meters per year, burying oases and ancient ruins, reshaping the desert in a slow, relentless march. Not all sand is quartz. In tropical regions, sand is often composed of calcium carbonate, the eroded remains of coral reefs and shell fragments. The white beaches of the Caribbean and the Maldives are carbonate sands, fine and soft, reflecting sunlight with dazzling intensity. In volcanic regions, sand is black, composed of basaltic glass and pyroclastic fragments. The beaches of Iceland and Hawaii are black sand beaches, their darkness absorbing heat, making them warm to the touch even in cool climates. Sand is also a record of its source. The mineral composition of sand grains reveals the rocks from which they were eroded. Quartz-rich sands indicate granitic or metamorphic source rocks. Feldspar-rich sands suggest recent volcanic activity or rapid erosion of young mountain ranges. Heavy minerals, zircon, garnet, magnetite, concentrate in placer deposits, sorted by density as rivers and waves winnow away the lighter grains. Gold is often found in placer deposits, eroded from quartz veins in the mountains, and concentrated in stream beds by the same processes that sort sand. The size of sand grains is also informative. Coarse sand indicates high-energy environments, fast-flowing rivers, wave-battered coastlines. Fine sand suggests lower energy. Slow rivers, sheltered bays, wind-blown deserts. The rounding of grains reflects the distance they have traveled and the intensity of abrasion. Angular grains are freshly eroded, not yet worn smooth. Well-rounded grains have been transported far from their source, tumbled and abraded until their edges are gone. Erosion is not uniform. Resistant rocks erode slowly, forming cliffs and ridges. Weak rocks erode quickly, forming valleys and lowlands. Differential erosion creates the dramatic landscapes of the American Southwest, mesas, buttes, and hoodoos, isolated pillars of rock capped by resistant layers that protect the softer rock below. When the cap rock is breached, the underlying material erodes rapidly, and the pillar collapses. The landscape is a graveyard of former mesas, their remnants scattered across the desert floor. Glaciers are the most powerful agents of erosion. A glacier is a river of ice, flowing under its own weight, grinding the bedrock beneath it into powder. The ice itself is not abrasive, but the rocks embedded in the base of the glacier act like sandpaper, scouring the bedrock and carving deep valleys. The valleys carved by glaciers are U-shaped, with steep walls and flat floors, distinct from the V-shaped valleys carved by rivers. Yosemite Valley is a glacial valley, carved by ice during the Pleistocene, its walls rising nearly a kilometer above the valley floor, polished smooth in places by the passage of ice. Glaciers also pluck rocks from the bedrock. As the ice flows over a bedrock obstacle, it freezes onto the downstream side, and when the glacier advances, it tears the rock away, leaving behind a jagged, stepped surface. This process, called plucking, is most effective on jointed or fractured rock. The combination of abrasion and plucking allows glaciers to erode bedrock at rates far exceeding those of rivers, carving deep fjords, cirques, and hanging valleys. When glaciers retreat, they leave behind a landscape transformed. Moraines mark the former extent of the ice, ridges of unsorted sediment deposited at the glacier's edge. Drumlins are streamlined hills of glacial till, shaped by the flow of ice. Eskers are sinuous ridges of sand and gravel, deposited by meltwater streams flowing beneath the glacier. Erratics are boulders, carried far from their source and deposited when the ice melted, sometimes perched incongruously on bedrock of a completely different type. The Great Lakes were carved by glaciers. During the Pleistocene, ice sheets advanced and retreated across North America multiple times, scouring out the basins that would become the lakes. The ice was over a kilometer thick, heavy enough to depress the Earth's crust beneath it. When the ice melted, the crust rebounded, but the rebound was not uniform, and the basins filled with meltwater, forming the largest group of freshwater lakes in the world. Glacial erosion also creates fjords, deep, narrow inlets carved by glaciers that flowed from the mountains to the sea. The fjords of Norway, Greenland, and New Zealand are drowned glacial valleys, their floors far below sea level, their walls rising steeply from the water. The deepest fjord, Skeleton Inlet in Antarctica, has a floor more than 1,900 meters below sea level, carved by ice flowing from the Antarctic ice sheet. Ice is not the only sculptor in cold climates. Freeze-thaw weathering fractures rock without the need for flowing ice. Water enters cracks, freezes expand by 9%, and exerts pressure sufficient to split the rock. Repeated freeze-thaw cycles break solid bedrock into angular fragments, creating talus slopes, piles of broken rock at the base of cliffs. In alpine regions, freeze-thaw weathering is the dominant erosional process, shaping the jagged peaks and knife-edge ridges of high mountains. Chemical weathering also sculpts the landscape, though more subtly. Rainwater, slightly acidic, reacts with minerals in the rock, dissolving some and altering others. Feldspar weathers to clay, olivine and pyroxene weather to iron oxides, giving weathered basalt a rusty red color. Granite weathers into rounded boulders, the corners and edges dissolving faster than the flat faces, a process called spheroidal weathering. Over millions of years, chemical weathering reduces mountains to soil, releasing nutrients that support plant life and carrying dissolved ions to the ocean. Soil itself is a product of erosion and weathering. It is not merely dirt, but a complex mixture of mineral particles, organic matter, water, air, and living organisms. Soil forms slowly, at rates measured in centimeters per 1,000 years. The thickness and composition of soil depend on climate, vegetation, parent rock, topography, and time. In tropical rainforests, heavy rainfall leaches nutrients from the soil, leaving behind iron and aluminum oxides in thick red laterite soils. In temperate regions, organic matter accumulates, forming dark, fertile soils. In deserts, soil is thin and poorly developed, with little organic matter and high concentrations of salts. Erosion removes soil faster than it forms in many regions. Agriculture accelerates erosion by removing vegetation and exposing the soil to wind and rain. The Dust Bowl of the 1930s was a catastrophic example. Decades of intensive farming in the Great Plains stripped the land of its protective grass cover, and when drought struck, the topsoil blew away in massive dust storms that darkened the skies and buried farms. The loss of topsoil is irreversible on human timescales. It takes centuries to millennia to rebuild what can be lost in a single season. Rivers carry the products of erosion to the sea. The sediment load of a river depends on the erodibility of the bedrock, the steepness of the terrain, the climate, and the presence of vegetation. The Amazon River carries over 1 billion tons of sediment to the Atlantic Ocean each year, eroded from the Andes and the Brazilian Shield. The Yellow River in China is named for the color of its sediment-laden water, carrying over 1 billion tons of loess, wind-deposited silt, from the lowest plateau to the Yellow Sea. Sediment does not simply vanish into the ocean. It accumulates on continental shelves, in river deltas, and in deep ocean basins, building new layers of sedimentary rock. The Mississippi River Delta has been building for thousands of years, advancing into the Gulf of Mexico, creating wetlands and barrier islands. The delta is not stable. Channels shift, sediment is redistributed, and the land subsides under the weight of accumulated sediment. Human intervention, levees, dams, channelization, has disrupted the natural processes, reducing sediment delivery and causing the delta to erode and sink. Erosion is also a climate regulator. The weathering of silicate rocks consumes carbon dioxide, locking it into carbonate minerals that are eventually subducted and returned to the mantle. The uplift of mountain ranges accelerates weathering by exposing fresh rock to the atmosphere and increasing precipitation. The Himalayas, still rising, are a major sink for atmospheric carbon dioxide, drawing down CO2 and contributing to the long-term cooling of the planet. This is the Ramo-Rudderman hypothesis, that the uplift of the Himalayas and the Tibetan Plateau over the past 50 million years has driven the global cooling that led to the current ice age. Erosion operates on all timescales. A single rainstorm can trigger a landslide, moving thousands of tons of rock in seconds. A river carves its valley over millions of years. Wind reshapes sand dunes daily, but the dunes themselves migrate over centuries. Glaciers advance and retreat over tens of thousands of years, carving landscapes that persist for millions. The interplay of these processes, operating at different rates and scales, creates the diversity of landforms that cover the Earth's surface. The sculptors of time are relentless. They do not rest. Every raindrop that falls, every gust of wind, every freeze-thaw cycle, every glacier that flows, each contributes to the reshaping of the planet. Mountains rise and are worn down. Continents are eroded and their sediments deposited in the oceans, only to be uplifted again as new mountains in the next tectonic cycle. The surface of the Earth is not permanent. It is a transient expression of the balance between construction and destruction, between the forces that build and the forces that tear down. And in the end, erosion wins. Given enough time, every mountain will be reduced to a plain, every canyon filled with sediment, every coastline smoothed by the waves. But the cycle does not end. New mountains will rise. New rivers will carve new valleys. The earth will continue its slow, patient work of creation and destruction, sculpting and resculpting the surface in an endless dance that has no beginning and no end, only the eternal present of geological time. Water remembers. It remembers the mountains from which it fell, the rocks through which it flowed, the ancient seas that evaporated to send it skyward again. Every river carries the chemical signature of its watershed. Every glacier preserves a record of past climates and layers of ice. Every flood leaves behind sediments that tell the story of catastrophic flows that reshaped continents in days. Water is not merely a solvent, a transporter of sediment, a carver of canyons. It is the planet's archivist, recording in its chemistry and its deposits the history of the Earth's surface over billions of years. Rivers are the arteries of continents, draining rainfall from vast watersheds and carrying it to the sea. The Amazon River discharges 200,000 cubic meters of water per second into the Atlantic Ocean, more than the next 7 largest rivers combined. Its watershed covers 7 million square kilometers, nearly 40% of South America, collecting rainfall from the Andes, the Brazilian Shield, and the rainforests of the basin. The water that flows past Manaus today fell as rain weeks or months ago, hundreds or thousands of kilometers upstream, filtered through soil, percolated through bedrock, emerged in springs, and joined the countless tributaries that feed the main channel. The chemistry of river water reveals its journey. Rainwater is nearly pure, but as it flows over and through rock, it dissolves minerals: calcium, magnesium, sodium, silica. Rivers draining limestone regions are rich in calcium and bicarbonate. Rivers draining granitic regions carry more silica and sodium. Rivers draining volcanic regions are enriched in iron and sulfur. The dissolved load is invisible, but it constitutes a significant fraction of the material transported by rivers, eventually precipitating in the ocean as carbonate sediments or incorporated into the shells and skeletons of marine organisms. Some rivers carry more sediment than water. The Yellow River in China, during peak flow, can be 40% sediment by volume, a churning slurry of loess eroded from the Loess Plateau. The sediment gives the river its color and its name. Over millennia, the river has built a vast delta and raised its bed above the surrounding floodplain. Confined by levees, prone to catastrophic floods when the levees fail, the river has changed course multiple times in recorded history, sometimes flowing north to the Bohai Sea, sometimes south to the Yellow Sea, each shift accompanied by devastating floods that drowned entire provinces. Rivers also remember ice ages. During glacial periods, sea levels dropped by over 100 meters as water was locked up in continental ice sheets. Rivers extended their courses across the exposed continental shelves, carving valleys that are now submerged. The Hudson River once flowed across what is now the continental shelf, cutting a deep canyon that extends far beyond the current river mouth. When the ice melted and sea levels rose, the lower valleys were drowned, forming estuaries: the Hudson River Estuary, the Chesapeake Bay, the mouth of the Amazon. These drowned river valleys are among the most productive ecosystems on Earth, mixing freshwater and saltwater, trapping nutrients, supporting fisheries and wetlands. Glaciers are rivers of ice, but they move far more slowly and carry a different kind of memory. Ice forms from compacted snow, layer upon layer accumulating over centuries. Each layer preserves a sample of the atmosphere at the time it fell. Air bubbles trapped in the ice contain ancient air with concentrations of carbon dioxide, methane, and other gases that reveal past climates. Ice cores drilled from the Greenland and Antarctic ice sheets extend back over 800,000 years, providing a continuous record of atmospheric composition, temperature, and volcanic activity. The deepest ice is the oldest. At the bottom of the Antarctic ice sheet, ice over 1 million years old lies compressed under the weight of 3 kilometers of overlying ice. The pressure is immense, the temperature just below the melting point. In some places, the ice is melting at the base, lubricating the flow of the glacier above. The meltwater flows beneath the ice, carving channels, forming subglacial lakes. Lake Vostok, buried beneath 4 kilometers of ice in East Antarctica, is one of the largest subglacial lakes, a body of liquid water the size of Lake Ontario, isolated from the surface for millions of years, possibly harboring microbial life adapted to the extreme cold and darkness. Glaciers advance and retreat in response to climate. During the Pleistocene, ice sheets advanced across North America, Europe, and Asia multiple times, covering vast areas in ice up to several kilometers thick. The ice scoured the landscape, carving valleys, depositing moraines, and redirecting rivers. When the ice retreated, it left behind a transformed geography. The Great Lakes, the fjords of Scandinavia, the drumlins and eskers of the northern plains. The most recent glacial maximum occurred around 20,000 years ago. Since then, the ice has been retreating, though remnants persist in Greenland, Antarctica, and high mountain ranges. The retreat is accelerating. Glaciers worldwide are losing mass, their termini receding, their surfaces thinning. The Greenland ice sheet is losing approximately 280 billion tons of ice per year, contributing to sea level rise. The Antarctic ice sheet is also losing mass, particularly in West Antarctica, where warming ocean water is melting the ice shelves from below, destabilizing the glaciers that flow into them. If the West Antarctic ice sheet were to collapse entirely, global sea levels would rise by over 3 meters, inundating coastal cities and displacing hundreds of millions of people. Ancient floods dwarf anything in human experience. The channeled scablands of eastern Washington are the result of catastrophic floods that occurred at the end of the last ice age. Glacial Lake Missoula, a massive lake dammed by ice in what is now Montana, repeatedly filled and burst, releasing floods of unimaginable scale. Each flood discharged more water than all the rivers on Earth combined, flowing at speeds exceeding 100 kilometers per hour, carving deep channels into the basalt bedrock, stripping away soil and depositing house-sized boulders hundreds of kilometers downstream. The floods occurred dozens of times over a period of several thousand years, each one reshaping the landscape in a matter of days. The evidence for these floods was controversial when first proposed in the 1920s. Geologists, trained in uniformitarianism, the principle that the present is the key to the past, resisted the idea of catastrophic events. But the evidence was undeniable. Giant ripples in gravel bars, enormous potholes scoured into bedrock, erratic boulders perched on hilltops, dry waterfalls where no rivers now flow. The channeled scablands are a landscape of catastrophe, frozen in time, a reminder that the Earth's history includes not only slow, gradual processes, but also sudden, violent events that reshape entire regions in geological instants. Similar megafloods occurred elsewhere. The Altai Mountains of Siberia were scoured by floods from glacial lakes that burst during deglaciation. The English Channel may have been carved in part by a catastrophic flood when a glacial lake dammed in the North Sea breached its ice dam and drained southward, severing Britain from continental Europe. The Black Sea was once a freshwater lake, isolated from the Mediterranean. Around 7,600 years ago, rising sea levels caused the Mediterranean to breach the Bosporus, flooding the Black Sea basin with salt water in what may have been a catastrophic inundation, raising the lake level by over 100 meters and drowning coastal settlements. This event may be the origin of flood myths in the region, preserved in oral traditions and later written into the Epic of Gilgamesh and the biblical account of Noah's flood. Water also remembers in the form of aquifers, underground reservoirs of water stored in porous rock. The Ogallala Aquifer beneath the Great Plains of the United States is one of the largest aquifers in the world, containing water that accumulated over thousands of years, much of it from meltwater at the end of the last ice age. The aquifer supports agriculture across 8 states, but it is being depleted faster than it is recharged. In some areas, the water table has dropped by over 50 meters, and wells are running dry. The water being pumped today is fossil water, ancient and irreplaceable on human timescales. The Great Artesian Basin in Australia is even larger, covering over 1.5 million square kilometers. The water in the basin is thousands to millions of years old, having infiltrated the sandstone aquifers during wetter climatic periods. The water is under pressure, and in some places it flows to the surface naturally, forming artesian springs that have supported life in the arid interior for millennia. Aboriginal Australians knew the locations of these springs and used them as waypoints in their travels across the desert. European settlers drilled bores to access the water, and thousands of artesian wells now tap the basin, though over-extraction has reduced the pressure, and many wells no longer flow. Groundwater is not static. It flows slowly through the pore spaces and fractures in rock, following the hydraulic gradient from areas of high pressure to areas of low pressure. The flow rate depends on the permeability of the rock. Sand and gravel are highly permeable, allowing water to flow quickly. Clay and shale are nearly impermeable, blocking flow. In karst regions, where limestone has been dissolved to form caves and conduits, groundwater can flow rapidly, emerging in large springs. The Silver Springs in Florida discharge over 20 cubic meters of water per second, sourced from the Floridan Aquifer, one of the most productive aquifers in the world. Groundwater also dissolves minerals, and in some cases it deposits them. Travertine is a form of limestone deposited by mineral-rich groundwater emerging at the surface. The terraces of Pamukkale in Turkey are travertine formations built up over thousands of years as calcium carbonate precipitates from hot springs flowing down the hillside. The terraces are white, stepped, and filled with shallow pools of turquoise water, a landscape that seems more sculpted than natural, though it is entirely the work of water and dissolved minerals. Hot springs are windows into the subsurface. Water heated by contact with hot rock or magma rises to the surface, carrying dissolved minerals and gases. The hot springs of Yellowstone are among the most famous, fed by a magma chamber that lies just a few kilometers beneath the surface. The water in these springs can exceed the boiling point, and the springs are often surrounded by colorful microbial mats, thermophilic bacteria, and archaea that thrive in the extreme heat. The colors are produced by pigments that protect the microbes from ultraviolet radiation and help them capture light for photosynthesis or chemosynthesis. Geysers are hot springs that erupt periodically, ejecting water and steam into the air. Old Faithful in Yellowstone erupts approximately every 90 minutes, shooting water up to 50 meters high. The eruption is driven by the buildup of pressure in an underground chamber. Water seeps into the chamber, is heated by the surrounding rock, and begins to boil. The steam cannot escape because the chamber is constricted, so pressure builds until it overcomes the weight of the overlying water, and the geyser erupts. After the eruption, the chamber refills, and the cycle begins again. Rivers also shape human history. Civilizations arose along rivers: the Nile, the Tigris and Euphrates, the Indus, the Yellow River, the Ganges. Rivers provided water for drinking and irrigation, transportation routes, and fertile floodplains enriched by annual floods. The Nile's floods were so regular that the ancient Egyptians based their calendar on them. The floods deposited nutrient-rich silt on the fields, ensuring bountiful harvests. The construction of the Aswan High Dam in the 1960s ended the annual floods, controlling the river for hydroelectric power and irrigation, but also trapping the sediment behind the dam, starving the delta of nutrients, and causing it to erode. Dams alter rivers profoundly. They trap sediment, change water temperature, block the migration of fish, and transform free-flowing rivers into a series of reservoirs. The Colorado River, once a wild sediment-laden torrent that carved the Grand Canyon, is now regulated by a series of dams. The river rarely reaches the sea. Its water is diverted for agriculture and urban use, and its delta, once a vast wetland teeming with life, is now largely dry. The sediment that once built the delta is trapped behind dams, accumulating in reservoirs, reducing their capacity. Rivers also carry pollution. Industrial waste, agricultural runoff, sewage all find their way into rivers and are carried downstream. The Ganges, sacred to Hindus, is one of the most polluted rivers in the world, contaminated with untreated sewage, industrial effluents, and the ashes of cremated bodies. The pollution poses serious health risks to the millions of people who depend on the river for drinking water, bathing, and irrigation. Efforts to clean the river have been ongoing for decades, but the scale of the problem is immense. Water is also a solvent of time. It erases the past, carrying away the evidence of ancient landscapes, dissolving mountains, filling valleys with sediment. But it also preserves the past, depositing layers of sediment that become sedimentary rock, trapping fossils, recording the conditions of deposition in the grain size, sorting, and composition of the sediments. The rock record is a library written in stone, and water is the scribe inscribing the history of the earth, one layer at a time. The water cycle is ancient. Water has been cycling between the oceans, the atmosphere, and the land for billions of years. The water you drink today has been part of this cycle since the earth first cooled enough for liquid water to condense on its surface. It has been ocean water, rain, river water, groundwater, ice, vapor. It has been inside living organisms, part of their cells, their blood, their sap. It has been locked in minerals, released by volcanism, subducted into the mantle, and returned to the surface. Water is not created or destroyed, only transformed, cycled endlessly through the Earth system. And water will continue to flow. Rivers will carve new valleys, glaciers will advance and retreat. Floods will reshape landscapes, groundwater will dissolve rock and deposit minerals. The memory of water will be written in sediments, in ice cores, in the chemistry of rivers and springs, preserving the history of the planet for as long as water exists on Earth. And when the sun expands into a red giant billions of years from now, and the oceans boil away into space, the memory of water will be the last thing to vanish, evaporating into the void, carrying with it the final traces of a world that was once alive. The ocean floor is not a featureless plain, but a landscape as varied and dramatic as any on the continents. Mountain ranges that dwarf the Himalayas, trenches deeper than Everest is tall, volcanic chains that stretch for thousands of kilometers, and fissures from which the planet's interior bleeds heat and minerals into the frigid darkness. This is the abyss, the deep ocean, a realm of crushing pressure and absolute night, where the Earth's geological processes operate hidden from the sun, indifferent to the life that clings to the surface far above. The deepest place on Earth is the Challenger Deep in the Mariana Trench, nearly 11 kilometers below sea level. The pressure here exceeds 1,000 atmospheres, enough to crush a human body instantly, to compress air-filled spaces to nothing. Yet life exists even here. Amphipods, snailfish, and microbial communities thrive in the sediments and water column, adapted to conditions that would be lethal to surface organisms. The trench is a subduction zone, where the Pacific Plate descends beneath the Philippine Plate, bending downward into the mantle, creating the deepest depression on the planet's surface. Trenches are the graveyards of oceanic crust. The seafloor, created at mid-ocean ridges, spreads outward, cools, and becomes denser. Eventually, it encounters a continental plate or another oceanic plate and begins to subduct, diving back into the mantle. The descending plate does not go quietly. It sticks, accumulates stress, and releases it in megathrust earthquakes, the most powerful seismic events on Earth. The 2011 Tohoku earthquake, which triggered the devastating tsunami that struck Japan, occurred along the Japan Trench, where the Pacific Plate subducts beneath the Eurasian Plate. The earthquake released energy equivalent to 600 million times the atomic bomb dropped on Hiroshima. As the oceanic plate descends, it carries with it water locked in hydrated minerals, trapped in sediments, absorbed into fractures. At depths of around 100 kilometers, the increasing temperature and pressure cause these minerals to break down, releasing water into the overlying mantle wedge. The water lowers the melting point of the mantle rock, triggering partial melting and generating magma. This magma rises, feeding the volcanic arcs that parallel the trenches, the Andes, the Cascades, the islands of Japan and Indonesia. The volcanoes are the surface expression of subduction, the visible consequence of the ocean floor's return to the mantle. Mid-ocean ridges are the birthplaces of oceanic crust. Here, tectonic plates pull apart and magma wells up from the mantle to fill the gap. The Mid-Atlantic Ridge, the East Pacific Rise, the Southwest Indian Ridge. These are the seams of the Earth, the places where new seafloor is continuously created. The ridges are not smooth but segmented, offset by transformed faults, punctuated by volcanic peaks and hydrothermal vents. The newly formed crust is basaltic, dark and fine-grained, erupted in pillow lavas that cool instantly upon contact with seawater. The discovery of hydrothermal vents in 1977 revolutionized our understanding of life and geology. These vents, found along mid-ocean ridges and in volcanic regions of the deep sea, are fissures in the seafloor from which superheated water erupts, laden with dissolved minerals. The water can exceed 400 degrees Celsius, but it does not boil because the pressure at depth is so great. As the hot water mixes with the frigid seawater, the dissolved minerals precipitate, forming chimneys of sulfide minerals, black smokers, so named for the dark plumes of mineral-rich water they emit. The chimneys grow rapidly, sometimes several meters per year, built up layer by layer as minerals precipitate from the vent fluids. They are fragile, prone to collapse, but new chimneys form continuously. The minerals deposited include pyrite, chalcopyrite, sphalerite and galena, iron, copper, zinc, and lead sulfides. These are the same minerals mined on land for their metal content, and the ancient seafloor deposits, now uplifted and exposed, are the source of many of the world's ore bodies. But the most remarkable discovery at hydrothermal vents was not geological but biological. Surrounding the vents are ecosystems unlike any other on Earth, thriving in total darkness, independent of photosynthesis. The base of the food chain is not plants but chemosynthetic bacteria, microbes that derive energy from the oxidation of hydrogen sulfide and other chemicals in the vent fluids. These bacteria form dense mats on the seafloor and live symbiotically within the tissues of larger organisms, giant tube worms, clams, mussels, and shrimp that cluster around the vents, feeding on the bacteria or on organic matter produced by them. The tube worms, Riftia pachyptila, can grow over 2 meters long. They have no mouth, no digestive system. Instead, they host chemosynthetic bacteria in a specialized organ called a trophosome. The bacteria convert hydrogen sulfide, oxygen, and carbon dioxide into organic compounds, which the worm absorbs. In return, the worm provides the bacteria with a stable environment and access to the chemicals they need. This symbiosis allows the tube worms to thrive in an environment that would be toxic to most life. Hydrothermal vents are ephemeral. They form, flourish, and die as the underlying magma chambers cool or as tectonic activity shifts. A vent field may be active for decades or centuries, then go dormant, its chimneys collapsing, its ecosystems dispersing. The organisms that depend on the vents must be able to colonize new vents as they form, dispersing their larvae across the deep ocean in search of the chemical signatures that indicate active venting. How they accomplish this over distances of hundreds or thousands of kilometers remains one of the mysteries of deep-sea biology. Not all hydrothermal systems are at mid-ocean ridges. Some occur in back arc basins, regions of seafloor spreading behind volcanic arcs, driven by the same subduction processes that create the arcs. Others occur at seamounts, underwater volcanoes that rise from the seafloor but do not reach the surface. The Hawaiian Islands are the tips of a massive volcanic chain, but the majority of the volcanoes are submerged, forming seamounts that dot the Pacific Ocean floor. Some of these seamounts host hydrothermal vents, their ecosystems isolated from other vent fields by vast expanses of abyssal plain. The abyssal plains are the flattest places on Earth, vast stretches of seafloor covered by fine sediment, clay, silt, and the remains of microscopic organisms that rain down from the surface waters. The sediment accumulates slowly, millimeters per 1,000 years, building layers that preserve a continuous record of ocean conditions over millions of years. Cores drilled from the abyssal plains reveal cycles of climate change, ice ages and interglacials, shifts in ocean circulation, and the impacts of asteroid strikes. The sediments of the abyssal plains are not uniform. They vary in composition depending on depth, latitude, and proximity to continents. In shallow regions, above the carbonate compensation depth, the sediments are rich in calcium carbonate. The shells are foraminifera and coccolithophores that settle from the surface. Below the carbonate compensation depth, around 4 to 5 kilometers, the pressure and the acidity of the water dissolve the carbonate, and the sediments are dominated by siliceous ooze, the remains of diatoms and radiolarians, or by red clay, the finest particles of wind-blown dust and volcanic ash. The red clay accumulates at rates of 1 millimeter per 1,000 years, the slowest sedimentation rate on Earth. A layer 1 meter thick represents 1 million years of deposition. The clay is not red because of iron oxide, as might be expected, but because of the oxidation of iron in the sediment over geological time. The clay is ancient, undisturbed, a geological archive of unparalleled continuity. Seamounts and oceanic plateaus rise from the abyssal plains, remnants of volcanic activity that occurred millions of years ago. The Ontong Java Plateau in the Western Pacific is the largest oceanic plateau, covering an area the size of Alaska, formed by a massive volcanic eruption around 120 million years ago. The eruption released enough lava to cover the entire United States in a layer 30 meters thick. The cause of such massive eruptions is debated, but they are likely related to mantle plumes, superheated upwellings from the deep mantle that punch through the oceanic crust and flood the surface with basalt. Seamounts are often colonized by deep-sea corals which build reefs in the cold, dark waters of the deep ocean. These corals do not rely on photosynthetic symbionts like their shallow water counterparts, but instead capture plankton and organic particles from the water. The reefs grow slowly, millimeters per year, and can persist for thousands of years, providing habitat for fish, crustaceans, and other organisms. Deep-sea trawling, however, has devastated many of these reefs, dragging heavy nets across the seafloor and destroying ecosystems that took millennia to develop. The ocean floor is also scarred by submarine landslides. some of them among the largest mass movements on Earth. The Storegga slide, which occurred off the coast of Norway around 8,200 years ago, involved the collapse of a section of the continental shelf, displacing an estimated 3,000 cubic kilometers of sediment. The slide triggered a tsunami that struck the coasts of Norway, Scotland, and Iceland, with wave heights exceeding 20 meters. Evidence of the tsunami has been found in coastal sediments, layers of sand deposited far inland by the waves, submarine canyons cut into the continental slopes carved by turbidity currents, underwater avalanches of sediment-laden water that flow down the slope at high speeds. These currents are triggered by earthquakes, storms, or the accumulation of unstable sediment on the shelf edge. As the turbidity current flows, it erodes the sea floor, carving deep canyons that rival the Grand Canyon in scale. The Monterey Canyon off the coast of California is over 1 kilometer deep and extends over 100 kilometers from the coast into the deep ocean. Turbidity currents deposit their sediment load on the abyssal plains, forming submarine fans, vast aprons of sediment that spread out from the mouths of canyons. The Bengal fan, fed by sediment from the Ganges and Brahmaputra rivers, is the largest submarine fan in the world, covering an area of 3 million square kilometers. The fan is built from sediment eroded from the Himalayas, carried down the rivers, and deposited on the continental shelf, then transported to the deep ocean by turbidity currents. The fan is over 16 kilometers thick in places, a massive accumulation of sediment that records the erosion of the world's highest mountains over the past 17 million years. The ocean floor is also a repository of meteorites. Meteorites that fall into the ocean sink to the sea floor and are buried by sediment. Because the ocean covers 70% of the Earth's surface, the majority of meteorites that strike the planet land in the ocean. Some of these meteorites are later recovered by dredging or deep-sea drilling, providing samples of extraterrestrial material that would otherwise be lost. Manganese nodules litter the abyssal plains, potato-sized lumps of metal oxides that form by the slow precipitation of manganese, iron, nickel, copper, and cobalt from seawater. The nodules grow at rates of millimeters per million years, among the slowest geological processes known. They form around a nucleus, a shark tooth, a fragment of bone, a piece of volcanic rock, and accrete layer by layer like tree rings, recording changes in ocean chemistry over millions of years. The nodules are a potential source of valuable metals, and there is interest in mining them, but the environmental impact of such mining is uncertain, and the technology is still in development. Methane hydrates, also known as methane clathrates, are another resource found on the ocean floor. These are ice-like solids in which methane molecules are trapped within a lattice of water molecules, stable only under high pressure and low temperature. Methane hydrates are found in seafloor sediments along continental margins and beneath permafrost in polar regions. The total amount of methane locked in hydrates is estimated to exceed all other fossil fuel reserves combined, but extracting it is difficult, and destabilizing the hydrates could release vast quantities of methane, a potent greenhouse gas, into the atmosphere, accelerating climate change. The ocean floor is also a graveyard of ships, aircraft, and other human artifacts. Thousands of shipwrecks lie on the seafloor, some of them centuries old, preserved in the cold, oxygen-poor waters of the deep ocean. The Titanic, resting at a depth of nearly 4 kilometers, is slowly being consumed by iron-oxidizing bacteria that form rusticles, icicle-like structures of rust hanging from the ship's hull. In a few decades, the ship will collapse entirely, reduced to a pile of rust and debris. The deep ocean is the least explored region of the planet. More people have walked on the moon than have descended to the deepest parts of the ocean. The pressure, the darkness, the remoteness all make exploration difficult and expensive. But the deep ocean is not empty. It is geologically active, biologically diverse, and intimately connected to the processes that shape the Earth's surface. The mid-ocean ridges create new crust. The trenches consume old crust. The hydrothermal vents support ecosystems that challenge our understanding of the limits of life. The sediments preserve a record of the planet's history. The abyss whispers, but few are listening. The ocean floor is a frontier, vast and largely unknown, holding secrets about the Earth's past, present and future. The whispers are faint, carried in the chemistry of vent fluids, the layers of sediment, the magnetic stripes of the seafloor, the fossils of deep-sea organisms. They speak of a planet in constant motion, of crust being created and destroyed, of life adapting to the most extreme environments, of processes that operate on timescales far beyond human experience. And the ocean continues its work, indifferent to observation, reshaping the seafloor, cycling water and minerals through the crust, hosting ecosystems that have existed for millions of years in darkness and silence. The abyss is patient. It has been here for billions of years, and it will remain long after the continents have eroded away, long after the last mountain has been leveled, long after the surface world has changed beyond recognition. Stone can be reborn, buried deep beneath mountains, subjected to pressures that would pulverize bone and temperatures that would vaporize flesh. Rock does not melt but transforms. The minerals recrystallize, realigning their atomic structures, forming new minerals stable under the new conditions. This is metamorphism, the alchemy of pressure and heat, the process by which sedimentary and igneous rocks are transformed into metamorphic rocks, their textures and compositions altered beyond recognition, yet their history preserved in the patterns of their foliation, the chemistry of their minerals, the ghosts of their former selves. Marble begins as limestone, a sedimentary rock composed of calcium carbonate, the compressed remains of ancient marine organisms, shells and skeletons that accumulated on the seafloor over millions of years. When limestone is buried and heated, the calcite crystals recrystallize, growing larger, interlocking, forming a dense crystalline rock that can be polished to a mirror finish. The transformation erases fossils, obliterates bedding, and creates a rock of pure uniform texture. The finest marble is white, nearly translucent, prized by sculptors for its workability and beauty. Michelangelo's David was carved from Carrara marble, quarried from the Apuan Alps of Tuscany, where limestone deposited in a shallow Jurassic sea was metamorphosed during the collision of tectonic plates that built the Apennine Mountains. Not all marble is white. Impurities in the original limestone produce color. Iron oxides create pink and red hues. Graphite and organic matter produce gray and black. Serpentine minerals create green veining. The swirling patterns in decorative marble are the result of differential metamorphism, where variations in composition, pressure, or temperature create zones of different mineral assemblages, preserved as bands and streaks when the rock is cut and polished. Slate begins as shale, a fine-grained sedimentary rock composed of clay minerals, deposited in quiet water lake beds, river deltas, deep ocean basins. When shale is subjected to low-grade metamorphism, the clay minerals recrystallize into mica, and the rock develops a property called slaty cleavage, the ability to split into thin, flat sheets along parallel planes. This cleavage is not related to the original bedding of the shale, but is imposed by the directional pressure of metamorphism, which aligns the mica crystals perpendicular to the direction of maximum stress. Slate has been used for roofing and flooring for centuries. The Welsh slate industry, centred in Snowdonia, produced millions of tons of slate during the 19th century, exported worldwide to roof the cities of the Industrial Revolution. The slate was split by hand, skilled workers using hammers and chisels to cleave the rock along its natural planes, producing sheets thin enough to be light, yet strong enough to withstand decades of weathering. The industry has declined, but the quarries remain. Vast terraced excavations carved into the mountainsides, monuments to the human exploitation of metamorphic rock. As metamorphism intensifies, slate transforms into phyllite, then schist, then gneiss. Each step represents an increase in temperature and pressure, a progression toward higher-grade metamorphism. Phyllite has a silky sheen, the result of slightly larger mica crystals that reflect light. Schist has visible mica flakes, often large enough to be plucked from the rock with fingers. Gneiss has distinct banding, alternating layers of light and dark minerals, the result of segregation during metamorphism, where minerals of different compositions migrate and concentrate into separate layers. Gneiss is the most common metamorphic rock in the continental crust. It forms the cores of ancient mountain ranges, the deep roots of continents, the basement rock upon which younger sediments are deposited. The Lewisian gneiss of Scotland is among the oldest rocks in Europe, with ages exceeding 3 billion years. It has been metamorphosed multiple times, each event overprinting the last, creating a complex history recorded in the textures and mineral assemblages of the rock. Reading this history requires careful analysis, mapping the distribution of minerals, measuring the orientations of foliations, dating the crystallization of zircon grains. Metamorphism is not uniform. It varies with depth, temperature, and the presence of fluids. Contact metamorphism occurs when magma intrudes into cooler rock, heating the surrounding material and causing recrystallization in a narrow zone around the intrusion. The metamorphosed rock, called a contact aureole, can be meters to kilometers wide, depending on the size of the intrusion and the temperature of the magma. Limestone metamorphosed by contact with granite becomes marble. Shale becomes hornfels, a hard, fine-grained rock that rings when struck. Regional metamorphism occurs over large areas, typically associated with mountain building and the collision of tectonic plates. The pressure and temperature increase with depth, and rocks buried tens of kilometers beneath the surface are subjected to conditions that transform them completely. The Himalayas are a region of active regional metamorphism, with rocks being buried, heated, and deformed as the Indian plate continues to collide with the Eurasian plate. The metamorphic rocks exposed in the high peaks of the range were once buried deep in the crust and have been exhumed by erosion as the mountains rose. Fluids play a critical role in metamorphism. Water, carbon dioxide, and other volatiles are released from minerals as they break down under heat and pressure. These fluids migrate through the rock, dissolving some minerals and precipitating others, facilitating chemical reactions that would otherwise proceed too slowly to be geologically significant. The fluids also lower the melting point of rock, and in some cases partial melting occurs, producing migmatites, rocks that are part metamorphic, part igneous, with veins and pods of granite intruding into gneiss. Eclogite is a high-pressure metamorphic rock, formed at depths greater than 50 kilometers where the pressure exceeds 15,000 atmospheres. It is composed of garnet and pyroxene, both dense minerals, giving eclogite a distinctive green and red appearance, and a density greater than that of the mantle. Eclogite forms when basaltic oceanic crust is subducted and metamorphosed at great depth. The transformation from basalt to eclogite increases the density of the rock, making it more likely to sink into the mantle, driving subduction. Eclogite is rarely found at the surface, but when it is, it indicates that the rock has been exhumed from great depth, brought to the surface by tectonic processes that are still not fully understood. Blue schist is another high-pressure, low-temperature metamorphic rock formed in subduction zones where oceanic crust is rapidly buried before it has time to heat up. The blue color comes from glaucophane, a sodium-rich amphibole that forms only under these specific conditions. Blue schist is a marker of ancient subduction zones, and its presence in mountain belts indicates that the rocks were once part of a descending oceanic plate. The Franciscan complex of California is a blue schist terrain, a chaotic assemblage of metamorphosed oceanic crust, sediments, and serpentized mantle rock scraped off the subducting plate and accreted onto the North American continent over the past 150 million years. Serpentinite is a metamorphic rock formed by the hydration of ultramafic rocks, peridotite from the mantle. When seawater infiltrates fractures in the oceanic crust and reaches the mantle below, it reacts with olivine and pyroxene, transforming them into serpentine minerals. The rock becomes soft, slippery, and greenish, with a texture resembling snakeskin, hence the name. Serpentinite is weak and acts as a lubricant in subduction zones, facilitating the descent of the oceanic plate. It is also the state rock of California, where it is exposed in the Coast Ranges and the Sierra Nevada foothills. Quartzite is metamorphosed sandstone, composed almost entirely of interlocking quartz grains. The original sand grains are fused together by recrystallization, creating a rock harder than the sandstone from which it formed. Quartzite is resistant to weathering and erosion, forming ridges and cliffs in metamorphic terrains. The Baraboo Range in Wisconsin is composed of Precambrian quartzite, over 1.7 billion years old, one of the oldest mountain ranges in North America, worn down by erosion, but still standing because of the durability of the rock. Amphibolite is a metamorphic rock rich in amphibole minerals, typically formed by the metamorphism of basalt or gabbro. It is dark, dense, and often has a weakly developed foliation. Amphibolite forms under intermediate pressures and temperatures, conditions common in the middle crust during regional metamorphism. It is a major component of the deep continental crust, though it is rarely exposed at the surface. Metamorphic rocks record the conditions of their formation. By analyzing the mineral assemblages, the specific combinations of minerals present in the rock, geologists can estimate the temperature and pressure at which the rock was metamorphosed. Different minerals are stable under different conditions, and the presence or absence of certain minerals provides constraints on the metamorphic history. Garnet, for example, forms at high pressures. Andalusite forms at low pressures and moderate temperatures. Kyanite forms at high pressures and high temperatures. By mapping the distribution of these minerals, geologists can reconstruct the pressure-temperature paths that rocks followed as they were buried, metamorphosed, and exhumed. This is the field of metamorphic petrology, the study of the origin, composition, and structure of metamorphic rocks. It is a detective story written in minerals, a puzzle solved by careful observation, chemical analysis, and thermodynamic modeling. The goal is to understand the tectonic processes that buried the rocks, the heat sources that metamorphosed them, and the mechanisms that brought them back to the surface. Some metamorphic rocks have been to the mantle and back. Ultra-high pressure metamorphic rocks contain minerals that form only at depths greater than 100 kilometers. Coesite, a high-pressure form of quartz, and diamond, formed from carbon in the subducted crust. These rocks were carried down into the mantle by subduction, metamorphosed under extreme conditions, and then exhumed, brought back to the surface by buoyancy-driven processes, or by the collision and thickening of the crust. The discovery of coesite and diamond in metamorphic rocks in the 1980s revolutionized our understanding of subduction and exhumation, demonstrating that continental crust can be subducted to mantle depths and returned to the surface within tens of millions of years. The exhumation of metamorphic rocks is as important as their burial. Erosion removes the overlying rock, bringing deeper rocks to the surface. Tectonic forces can also exhume rocks, thrusting them upward along faults, or doming them upward in response to the removal of overlying material. The Black Hills of South Dakota are a dome of Precambrian metamorphic and igneous rocks, uplifted and exposed by erosion. surrounded by younger sedimentary rocks that once covered them. Metamorphic rocks are also economically important. Marble is quarried for building stone and sculpture. Slate is used for roofing and flooring. Talc, a soft metamorphic mineral, is used in cosmetics, ceramics, and paper. Graphite, formed by the metamorphism of organic-rich sediments, is used in lubricants, batteries, and pencils. Asbestos, a fibrous metamorphic mineral, was once widely used for insulation and fireproofing, though its use has been largely discontinued due to health risks. Metamorphic rocks also host ore deposits. Gold is often found in metamorphosed volcanic rocks, concentrated by hydrothermal fluids during metamorphism. The Witwatersrand Basin in South Africa, the largest gold deposit in the world, is a metamorphosed sedimentary basin where gold was concentrated in ancient river gravels and later remobilized by metamorphic fluids. Copper, zinc, and lead are also found in metamorphic rocks, often associated with metamorphosed volcanic sequences. The study of metamorphic rocks provides insights into the deep processes of the Earth, the conditions in the crust and mantle, the forces that build mountains and shape continents. Metamorphic rocks are the archives of tectonic history, recording the collisions of continents, the subduction of oceanic plates, the opening and closing of ocean basins. They are the witnesses to the slow, patient work of the Earth's interior, transforming rock under pressures and temperatures beyond human experience, creating new minerals, new textures, new rocks from old. And the transformation continues. Deep beneath the surface, rocks are being buried, heated, and metamorphosed. Limestone is becoming marble. Shale is becoming slate. Basalt is becoming ecologite. The alchemy of pressure is ongoing, operating on timescales of millions of years, reshaping the crust, recycling the materials of the Earth, creating the diversity of rocks that compose the continents and the ocean floor. Metamorphic rocks do not announce their origins. They are silent, their histories encrypted in the orientations of crystals, the compositions of minerals, the patterns of foliation. But with careful study, the stories can be read, stories of burial and exhumation, of heat and pressure, of tectonic forces that have shaped the planet for billions of years. The rocks remember. They carry within them the memory of the depths, the conditions under which they were transformed, the journey from the surface to the mantle and back again. And when the rocks are brought to the surface, when they are exposed by erosion or uplift, they reveal their secrets to those who know how to look. The banding of gneiss, the cleavage of slate, the crystalline texture of marble, each is a clue, a piece of the puzzle, a fragment of the Earth's deep history brought into the light. The Earth is not native to this place. Every atom in the planet's core, every grain of sand on its beaches, every molecule of water in its oceans, all of it came from somewhere else, forged in the furnaces of dying stars, scattered across the galaxy by supernova explosions, and swept up by gravity into the swirling disk of gas and dust that would become the solar system. The ground beneath your feet is stardust, condensed and compressed over 4.5 billion years, a cosmic inheritance from stars that died before the sun was born. Stars are the alchemists of the universe. In their cores, hydrogen fuses into helium, releasing energy that makes them shine. As stars age, they fuse helium into carbon, carbon into oxygen, oxygen into neon, silicon, sulfur, and eventually iron. Each fusion reaction releases energy, but iron is the end of the line. Fusing iron consumes energy rather than releasing it. So when a massive star's core becomes iron, fusion stops, the core collapses in a fraction of a second, and the outer layers rebound in a supernova explosion, a blast so powerful it briefly outshines an entire galaxy. In the extreme conditions of a supernova, elements heavier than iron are synthesized: gold, platinum, uranium, thorium. These elements cannot be created in the steady burning of a star's core, but require the intense neutron flux of a supernova, or the collision of neutron stars. Every gold ring, every uranium atom in the Earth's core, every lead isotope used to date ancient rocks, all were created in these cataclysmic events, and then dispersed into space, seeding the interstellar medium with the raw materials for new stars, new planets, new worlds. The solar system formed from a molecular cloud, a vast region of gas and dust drifting through the galaxy. Around 4.5 billion years ago, something disturbed the cloud, perhaps the shock wave from a nearby supernova. The cloud began to collapse under its own gravity, spinning faster as it contracted, flattening into a disk. At the center, the density and temperature increased until nuclear fusion ignited, and the sun was born. In the disk around the young sun, dust grains collided and stuck together, growing into pebbles, boulders, and eventually planetesimals, objects kilometers in size. The planetesimals collided, merging into larger bodies. In the inner solar system, where temperatures were high, only materials with high melting points could condense, metals and silicates. In the outer solar system, beyond the frost line, water, ice, and other volatiles could condense, allowing the formation of much larger bodies. The inner planets, Mercury, Venus, Earth, Mars, are small and rocky. The outer planets, Jupiter, Saturn, Uranus, Neptune, are massive and composed largely of hydrogen, helium, and ices. Earth formed through accretion, the gradual accumulation of planetesimals over tens of millions of years. The collisions were violent, releasing energy as heat. The planet was molten, a sphere of magma glowing red in the darkness of space. Heavy elements, iron and nickel, sank to the center, forming the core. Lighter elements, silicon, oxygen, magnesium, floated to the surface, forming the mantle and crust. This differentiation occurred early, within the first 100 million years of the planet's existence, and it is the reason the Earth has a layered structure. The Moon formed from a collision around 4.5 billion years ago. A Mars-sized body, sometimes called Theia, struck the young Earth in a glancing blow. The impact vaporized both Theia and a large portion of Earth's mantle, ejecting debris into orbit. The debris coalesced into the Moon. This giant impact hypothesis explains several features of the Earth-Moon system: the Moon's low density, its lack of a significant iron core, the similarity in isotopic composition between Earth and Moon rocks, and the high angular momentum of the Earth-Moon system. Meteorites are fragments of the early solar system, remnants of planetesimals that never accreted into planets. They fall to Earth constantly, most of them small, burning up in the atmosphere as meteors. A few survive the passage and reach the surface. These meteorites are windows into the past, samples of the material from which the planets formed, largely unchanged since the solar system's birth. There are three main types of meteorites. Stony meteorites, or chondrites, are composed of silicate minerals and are the most common. They contain chondrules, small spherical grains that formed by the rapid cooling of molten droplets in the solar nebula. Chondrules are among the oldest solid materials in the solar system, with ages of 4.567 billion years. Iron meteorites are composed of iron-nickel alloy and are fragments of the cores of differentiated planetesimals that were shattered by collisions. Stony iron meteorites are mixtures of silicate and metal, representing the boundary between the core and mantle of these disrupted bodies. Some meteorites contain pre-solar grains, microscopic particles that predate the solar system, formed in the atmospheres of other stars, and incorporated into the solar nebula without being vaporized. These grains have isotopic compositions that differ from solar system materials, fingerprints of the stars in which they formed. By studying pre-solar grains, scientists can learn about the types of stars that contributed material to the solar nebula and the nucleosynthetic processes that created the elements. Meteorites also contain organic compounds, amino acids, sugars, nucleobases, the building blocks of life. The Murchison meteorite, which fell in Australia in 1969, contains over 70 different amino acids, most of them not found in terrestrial life. This suggests that the raw materials for life were present in the early solar system and may have been delivered to Earth by meteorites and comets, seeding the planet with the molecules necessary for the origin of life. The Earth was bombarded heavily during its first few 100 million years, a period known as the Late Heavy Bombardment. Asteroids and comets struck the surface with such frequency that the crust was repeatedly melted and reformed. The impacts delivered water, organic compounds, and volatiles, contributing to the formation of the oceans and atmosphere. The bombardment declined around 3.8 billion years ago, allowing the surface to cool and solidify, creating stable conditions for the emergence of life. Impact craters are scars of this violent past. The Moon's surface is saturated with craters, preserving a record of the bombardment because the Moon has no atmosphere or tectonic activity to erase them. Earth's surface is geologically active, and most ancient craters have been erased by erosion, subduction, and volcanism. But some remain. The Vredefort crater in South Africa, formed 2 billion years ago, is the largest confirmed impact structure on Earth, over 300 kilometers in diameter. The Chicxulub crater in Mexico, formed 60 to 6 million years ago, is the impact that ended the age of dinosaurs, triggering mass extinction and reshaping the course of evolution. Impacts are not merely destructive, they also create. The heat and pressure of an impact can metamorphose rock, creating shocked quartz and other high-pressure minerals. Impacts can also melt rock, forming impact glass, and breccias, mixtures of shattered and melted material. Some impact craters contain valuable mineral deposits, concentrated by the heat and hydrothermal activity generated by the impact. The Sudbury Basin in Canada, one of the largest impact structures on Earth, hosts one of the world's richest nickel and copper deposits. The Earth continues to be struck by meteorites, though the rate is much lower than in the early solar system. Small meteorites fall daily, most of them unnoticed. Larger impacts are rare but inevitable. The Tunguska event in 1908, in which an asteroid or comet exploded in the atmosphere over Siberia, flattened 2,000 square kilometers of forest. The Chelyabinsk meteor in 2013 exploded over Russia, releasing energy equivalent to 30 Hiroshima bombs and injuring over 1,000 people from shattered glass. These events are reminders that the Earth is not isolated, but part of a dynamic solar system, still subject to the same processes that shaped it billions of years ago. Asteroids are the leftover building blocks of the solar system, concentrated in the asteroid belt between Mars and Jupiter. They range in size from boulders to bodies hundreds of kilometers across. Some asteroids are primitive, composed of carbonaceous material rich in water and organics. Others are differentiated, fragments of larger bodies that melted and separated into cores and mantles before being shattered by collisions. The asteroid Vesta, one of the largest in the belt, is a differentiated body with a basaltic crust, and meteorites from Vesta have been identified on Earth, providing samples of a world that never became a planet. Comets are visitors from the outer solar system, composed of ice, dust, and organic compounds. They originate in the Kuiper belt, beyond Neptune, or in the Oort cloud, a vast spherical shell of icy bodies surrounding the solar system at distances up to a light year from the Sun. When a comet's orbit brings it close to the Sun, the ice sublimates, releasing gas and dust that form a glowing coma and a tail stretching millions of kilometers. Comets may have delivered much of Earth's water, though the isotopic composition of cometary water does not always match that of Earth's oceans, suggesting that asteroids also contributed. The Earth is made of stardust, but it is also made of time. The atoms in your body have been part of stars, part of the solar nebula, part of planetesimals, part of the early Earth, part of the oceans, the atmosphere, the crust. They have been cycled through the mantle, subducted and returned to the surface, eroded and deposited, incorporated into living organisms, released back into the environment. The carbon in your cells was once carbon dioxide in the atmosphere, then part of a plant, then part of an animal, then returned to the atmosphere, then dissolved in the ocean, then precipitated as limestone, then subducted, then released by a volcano, then breathed in by you. The atoms are ancient, but their configurations are temporary, constantly rearranged by the processes of geology, chemistry, and biology. The Earth is 4.54 billion years old, dated by radiometric methods using the decay of uranium to lead in zircon crystals and the isotopic composition of meteorites. The oldest rocks on Earth, around 4 billion years old, found in the Canadian Shield in Western Australia. The oldest minerals are zircon grains from the Jack Hills of Australia, dated to 4.4 billion years, formed just 100 million years after the planet itself. These ancient zircons contain inclusions of other minerals that suggest the presence of liquid water on the surface at that time, indicating that the Earth cooled and formed a crust and oceans much earlier than previously thought. The Earth is a closed system for most elements, neither gaining nor losing significant amounts except for hydrogen and helium, which escape to space, and meteoritic material, which adds a few tens of thousands of tons per year. The elements are recycled endlessly, subducted into the mantle, returned to the surface by volcanism, eroded and deposited, metamorphosed and melted, the rock cycle, the water cycle, the carbon cycle, all are expressions of this recycling, driven by the heat of the Earth's interior and the energy of the sun. The sun will not shine forever. In about 5 billion years, it will exhaust its hydrogen fuel and begin to fuse helium, expanding into a red giant. The inner planets, including Earth, will be engulfed or scorched to lifeless cinders. The oceans will boil away. The atmosphere will be stripped. The crust will melt. The Earth will end as it began, a molten sphere, glowing in the darkness, its geological history erased, its memory lost. But for now, the Earth endures. The core spins, generating the magnetic field. The mantle convects, driving plate tectonics. The surface is shaped by erosion, volcanism, and the slow drift of continents. Water cycles through the atmosphere, the oceans, and the crust. Life persists, adapting, evolving, reshaping the surface in ways that geology alone cannot. The Earth is alive, dynamic, a planet in motion, a world shaped by 4.5 billion years of cosmic and geological processes. And tonight, as you rest, the Earth continues its work. The mantle flows, the plates drift, rivers carve valleys, glaciers grind bedrock, crystals grow in darkness, meteorites fall from the sky. The planet remembers its origins, written in the isotopes of its rocks, the chemistry of its minerals, the craters on its surface. The Earth is a fragment of the cosmos, a world built from the remnants of dead stars, a place where stardust became stone, where geology and time have conspired to create a surface diverse and beautiful, ancient and ever-changing. The floor you stand on is not solid ground. It is the frozen surface of a 4 billion year old river of fire. And the Earth, patient and enduring, will continue to whisper its secrets long after the last human voice has fallen silent, long after the continents have eroded to plains, long after the continents have drifted into new configurations. The whispers will continue, carried in the slow movement of tectonic plates, the crystallization of minerals, the fall of rain, the flow of rivers, the eternal dance of creation and destruction that has defined this planet since its birth.